start by thanking the organizers for this interesting meeting and for inviting me. So I'll talk today about the HISH holography-inspired stringy hadron model, and I'll discuss spectra, decay processes, and exotic hadrons. Most of the work is done in collaboration with my former student, Doreen Weissman. So the idea is to construct a unitary phenomenological string model that is in accordance with as much as possible experimental data of hadron physics, and also to predict some new phenomena. The model is in flat 4 dimensions, but it is inspired by a string thin holography. Eventually, the challenge is to relate it to QCD. The construction of the HISH model is based on the following steps. So the first step is we determine a confining holographic background with flavor bands. Then step 2, we analyze classical strings that correspond to mesons, baryons, glue balls, and so on in the confining holographic backgrounds. Step 3, we propose a map from the classical holographic strings to, in particular, rotating string to strings in flat 4 dimensions and with NC equal to 3. Step 4, we quantize the fluctuations of the classical string. It's hard to quantize it in the holographic setup, so we quantize it after performing the map in flat 4 dimensions. And this is subjected to boundary conditions that correspond to dressing the endpoints of the string with masses, baryonic vertices, charges, spins, etc. Then step 5 is to perform a normalization of the worldsheet Hamiltonian, and this cannot be done using the zeta function, the normalization. So we are using another method of using a contour integral and the Casimir-like method. In that way, we determine the intercept, including the contribution from the Liouville mode. Step 6, we confront the outcome of this model with experimental data and extract best fit values for the string tension, endpoint masses, and intercept for the various trajectories. Step 7, we use holography to compute strong decay processes, the total widths and branching ratios, and this is basically based on the string breaking process. And step 8, we analyze the stringy glue balls and exotics. Step 9, which I'll skip, I won't discuss today, is determining the scattering amplitude using string amplitudes a la Veneziana with weighted average scale-dependent string tension. This is a work that we have done recently where we showed that one can go from a string amplitude to a pertonic one. And finally, step 10 is to predict states and widths of unknown states. Okay, so step 1, we use the Wilson-Malsena line as a measure of confinement. If the renormalized action of the classical string is linear with the length, as it is here, then one can show that it corresponds to a confining boundary theory. For instance, in the ADS itself, this will be the profile of this Wilson-Malsena line, and of course, it's non-confining. Okay, so for a general metric that depends on the holographic coordinate of the following form, we found sufficient conditions for confining Wilson line, and there are the following. One possibility is that this quantity f squared, which is g00 times gxx, if it has a minimum and its value at the minimum is positive, then it's confined. The string tension is proportional to this quantity. So if it's not zero, it is a signal of confinement. And another possibility is that the quantity g00 times guu, that's the metric of the holographic direction, if it diverges, and at the point of divergence, this quantity f is positive, then again, it's confining. There are several such backgrounds like the Klebanov-Strassler and Baldassena-Nunes. They follow this first condition, and Witten's model or the Witten-Sakai-Sugimoto model follow the second condition. Now, just to illustrate the Witten's model, we have a 10-dimensional background with a four flat direction, one compact space direction, which together with the holographic direction forms a cigar, and U-dependent radius of an S4. And that has indeed a Wilson line that flattens down, and therefore it's linear with L, and it's confining. Now we add, this is very familiar, I know, but I just want to mention it. We add flavor brains. So in this case, we add D8 and anti-D8 brains. So in this cigar, it looks like adding, on the left, we'll have a UNF left symmetry and UNF right symmetry, which is spontaneously broken geometrically in the infrared into UNF diagonal. And so this is the original Sakai Sugimoto, and this is some generalization where it's not necessarily antipodal. Okay, so next step, we want to analyze stringy classical strings in these backgrounds, and it will be done in a model-independent way. I want to mention that usually in holography, we talk about a correspondence between bulk fields and operators on the boundary field, but well, that is of course based on the alpha prime goes to zero limit. But here we want to claim that to understand the spectra, decay widths, and scattering amplitudes, this can be done like only if we use holographic string hadrons and not fields in the bulk. Okay, so let's start with an ordinary rotating string configuration in this holographic background. So the string starts from some flavor burn and ends on a flavor burn, not necessarily the same one. You solve the Nabu-Goto action in that background, you get some profile for a rotating string. And for instance, in the generalized Sakai Sugimoto model, it will mean that there is a string that connects in one point the tip of the stack of flavor burns to the tip at the second point, and this whole string rotates. For instance, a B meson will have the form of a string that starts from the B flavor burn. It falls down to the wall, stretches, and comes up to a point on the UD flavor burn. So that was a meson. What about the baryon? So since a quark corresponds to n end of a string, the baryon has to be a structure that corresponds to NC strings. The proposed baryonic vertex in holography is based on a wrapped DP brane that wraps the p cycle. And because of the Ramond-Ramond flux in the background, the wrapped brane has to be connected to NC strings. So a cartoon of that, so we have this wrapped brane and there are NC strings connecting to some flavor brane. There are several possible layouts for these strings. And of course, one has to determine the preferred one using the lowest energy, but it can be in a symmetric way, or it can be the totally asymmetric way, where we have a quark on one side and the baryonic vertex connected to NC-1 quark on the other side. And now I'll come back to blue balls later. So now let me sketch, that's the main point. What is the HISH map? How do we go from these holographic classical strings to strings in 4 dimensions? So one can check the equations of motion of this system for a rotating string and the equation of motion for this system of a string, this massive endpoint in flat 4 dimensions. And one can realize that the equations of motion are the same, provided that we define the string endpoint quark mass. And so the quantity of this string endpoint is just the action associated with the vertical segments. Of course, this vertical horizontal is an approximation, but in this approximation, which is better the longer the string are, this is the way that we define the string endpoint mass. And then if we plug it into the boundary equations of motion, they take the form for a rotating string in this equation, which is just the balancing of the tension with the centrifugal force. And that is the basic map for rotating string between of holographic backgrounds and strings in flat 4 dimensions. Now, if you analyze now in 4 dimensions classical strings with massive endpoints, then you'll find that the energy as a function of the masses, the length, and the velocity is given in this expression, and the angular momentum in this expression. In general, we cannot eliminate the length, so we cannot get a Regge-like expression, but for the for the cases for small masses where beta I goes to 1, then we get that the modified Regge trajectory is alpha prime m squared times this quantity, which is deviates by the masses of the endpoints over the total mass to the power 3/2. And for a very large mass, we get that the expression is the total mass minus the masses of the endpoint to the 3/2. Okay, so what we have here is that in holography, there will be this kind of a configuration, and it will map in HISH into a string with massive endpoint. For the baryons, we can either have the symmetric case of a Y-shaped configuration with the strings that connect the baryonic vertex with the 3 endpoints on the flavor brand, and that maps in the HISH to a flat Y-shaped object. And this is the opposite asymmetric case where in NC equal to 3, it's a quark on one side and a diquark on the other side. So this is exactly what I just said. In NC equal to 3, we have either Y-shape or a quark diquark. And it turns out it was shown by Schaub and Proof that the classical Y-shape is unstable. An arm that is slightly shortened will eventually shrink to 0 side. We also checked it numerically, and we found this instability, which is not a perturbative instability. Now, it's easy now to write down the configuration for light quarks for all possible mesons and all possible baryons. Now, the harder steps are the quantization. So we talk now briefly, very briefly. That will take the whole lecture to explain how we did it, but I'll just mention the final result of the quantization of a string with massive and charged endpoints and the normalization and the computing of the intercept. So with massless endpoints, the classical trajectory goes into the quantum trajectory by adding the intercept, or for an excited state, it will be n plus j goes into alpha prime m squared plus a, where a is the intercept, which is related to the Casimir energy. So the Casimir energy is the sum of the eigenfrequencies for a massless string, just the sum over m. Using the theta function, we get this expression, and that relates to the, and that's the definition of the intercept. Now, for a massive endpoints, the eigenfrequencies are not anymore n. They have to be, there are solutions of this transcendental equation where Q is m, the mass endpoint over TL. This is assuming that the masses are the same. And the eigenfrequencies looks in the following way as a function of TL over m. So that will be a very massive endpoints, and this will be massless. So we see that we go from one value. For instance, here for the massless case, it's simply the values are n, and they will climb up for the very massive one to n plus 1. Okay, now to quantize the rotating springs in general, it's basically impossible, but in the limits of small and large masses, it's doable, and so we have done it for the small masses. The reason is that with the massive endpoints, the string is not free anymore, and it's interacting. Now, as I mentioned, we cannot use the zeta function renormalization. So instead, we convert the sum of the eigenfrequencies into a contour integral, and then we do a Casimir-like approach. We subtract the Casimir force of a string of length L from the strings of infinitely long string, and then we get the final answer for the intercept is that there are contributions from the transverse mode, d-3 transverse mode, one planar mode. Transverse means transverse to the plane of rotation. This is the planar mode, and this is the contribution from the Liouville or Polchinski-Strominger contribution that one needs to add since we are not in the critical dimension. And so this is the full expression that one gets for the intercept for the string with massive. Here I didn't put the charges, only masses at the endpoints. And the description of this intercept, the contribution of the transverse mode, the planar, Polchinski-Strasse, and the total. For the planar, there is something which is very interesting. This black line here is the border between values which are positive and negative. Getting negative intercept is very crucial, as I will argue in a moment, but we can get it from the transverse, not from these other contributions. Okay, so now I'm talking about fitting to experimental data and extracting the physical parameters. So it's easy to realize that in nature, this quantity A minus S, so the intercept minus the spin, which is the value which is relevant to the rotating string, to the orbital string, is always negative. You can check it for the trajectory for all the bosons and all the mesons and baryons. And for instance, for the rho, the intercept is close to 0.5, so this quantity is minus 0.5. Now, the attempt to explain this...
May I ask you, because what you call intercept in your calculation, this is really correction to leading edge trajectory at large J.
At large L, large orbital angular momentum, yes.
Like either large L or large
yes,
J.
Yes.
And so when you compare it now for rho meson, well, let's stay very close to like that's small J. So kind of this it's not really this difference doesn't really correspond to the quantity which you calculate.
Well, I'll show you in a second. I'll show you in a second the fits. They will see that it works well also for short strings. Wait a second. Okay, so I want to emphasize that we don't have a fully satisfactory way to get this negative intercept, and I consider this one of the most important questions in this business. Okay, so now, so let me show you now this fit that we do. So we start from rho and pi for isospin triplet, and so this blue dots are the experimental values, and this is the line. For the very light, you see it's linear, almost linear, but what's going on? Okay, so for some reason, I don't know, I cannot get all of them, but this is, we did the fit of all the trajectories. Here are the cases of the charmed one, and these are, I think, in fact, more interesting because here, when the quarks start to be heavy, you see that they are not anymore linear, they are bending. And so let me go back. If I can, oh shit, what's going on? Okay, this is for B. So the vector B star, and B star, and so I'm sorry that I don't have all these fits here, but these were for the mesons. For nucleons, we get similar fits. For the nucleons itself, so I meant for the baryon. For the nucleons itself, there is a feature which is well known in the game, that there is two different intercepts for the even and for the odd angular momenta. So this is for the lambda, and this is for the sigma. I do it very quickly, but you can see that in general the fits are very good, and this is all based on some values that so the best fit values that we extracted from these fits are that the masses, the so-called string endpoint masses, are not QCD masses, neither constituent quark masses, but rather it comes out that this is the light ones are around 60 MeV and 220, and this then goes back to what in the other models one gets. The slope is 0.9, and these are the values of the intercept for the various trajectories, and in particular, you can see this quantity A minus S for all these combinations. Both the vector and the scalar mesons are always negative. Okay, so let me proceed. Okay. I see that I have a problem with this PDF file. Maybe I will move to let me see if instead I can use this. Can you see this? Can you see this slide?
Yes, yes.
Okay. So so let me use instead this. Okay. Just a second. I'll go back to this point where we're. Okay. So these were the fits that I showed you and the values that we extracted. Now, the next step is not only to discuss the spectra, but rather also the decay processes. And this is, I want to mention something that is not done in other approaches. And for instance, decay processes of excited nucleons in the sphere model and so on. So let me show you what how do we treat it in this approach. So so the decay of a hadron in this model is essentially the breaking of a string into two strings. A type 1 open string can undergo a split. That's very well known. In our case, the string has a massive endpoint, so one has to change slightly the rules, but it's basically the same process. Now, the total decay, which is related to by the optical theorem to the imaginary part of the self-energy. Now, Polchinski and collaborators, they devised an interesting trick. Instead of calculating the unused open string diagram, they compactify one space direction, and then the amplitude is of this string wrapping the compactified direction. It opens up and then it's closed again. So it's a closed going into closed via an open, and that translates basically to a disk amplitude with two closed ring vertex operators. And they perform the calculation of that, and in particular, one can determine the dependence on the length of that. So the length appears from the zero modes, from the normalization, and from the computation of the expectation value of the vertex operators. The final answer is that, well, that's not very surprising, because intuitively we understand that the string can break at any point, and therefore the total width is linear with L. It is in fact the tension times L, and the length is a function of the total mass and the masses of the endpoints. So that's the value that one gets for long strings. For shorter ones, one has to take into account also a phase space factor, which is a function of the original mass and the two daughter masses. And so that was the expression for the total decay widths, which I'll show you in a second, the comparison to data. But we want also to understand individual processes. So how does in holography can the string break? It cannot break unless it is it hits a flavor brain. So the string fluctuates when it hits a flavor brain. It can then break into two strings, and this calculation of the fluctuation we have done in the past, and we came out with a result that they thought that this partial weight, sorry, the partial width is proportional to the e to the minus m squared. That's the mass of the pair of quarks that has been created at the breaking point over T. And one has to address it also with massive endpoint correction. So let me show you now something that's not common, this kind of comparison. So we took the trajectory, of various mesons, and also we did for baryons, and we looked on the width of excited states down to the ground states. And the prediction was that it will be of the form with some constant coefficient. If you want, that's a string coupling squared. And indeed, it comes out, at least for the light quarks, very close to a constant value, which is 0.1. And this is the chi-squared value. And then for higher, more massive one, there is a deviation of up to 25%. But the fact that for light quarks, we get that the total width is indeed proportional to T times L is quite impressive. Then you can, we did it, you cannot see it now, but we did this is the decay width as a function of the angular momentum for various mesons, and there is here not so great fit as the spectra. There are some exceptional states, but we get a pretty good agreement between the decay widths of the various angular momentum. Okay, I want to make one short remark. There is a basic difference between the states of this hadronic string and the ordinary open string. The ground state is for us not a tachyon, because we have massive endpoints and we have a negative intercept, and the spin one is not massless. It's a massive vector meson rather than the gauge field. Okay, so now, how much time do I have, Sergey? Sergey? Do you hear me?
Yeah. Technically, you're out of time, but we have time for questions. But yeah,
okay, so let's take a few more minutes to describe this part, which is maybe more related to topics that we discussed in this workshop. So I want to discuss now.
Cobi, may I ask a quick question?
Yes.
Then you say there is some kind of a mass attached to the associated with the endpoint of each string. If you
Yes.
deal with the light quarks, what this mass is? Is it?
I showed you. It's about 60 MeV.
60 MeV. So it's
Yes.
not their chiral mass. It's kind of an effective mass, right?
Exactly. Yes. Something in between. Okay. So yes.
Okay. Chiral phenomena are not included. I understand that. Okay.
Okay. So now let me talk a little bit about global states. So the globals will be necessarily closed strings. Okay. So in holography, it will be some closed string that rotates close to the wall, and it will map to simply a closed string in 4 dimensions. Now, the point that for closed string, this is very well known, that we have the tension is twice the tension of an open string, because it's the folded string is like essentially 2 strings, and so the slope is half, and the intercept is twice the intercept of an open string. Okay. Now we took all the flavorless hadrons, the F0 with 0++, and the F2 with 2++. And so there are, a handful candidates, and we try to see if we can match them, put them all in a meson trajectory. and if not, whether some of them will fit a global trajectory. So let me show you the picture. So these are meson trajectory, but there are two states. Here it's at 1380, we take as a ground state of the global, and another state, second one, which is 2060, and that has a slope of half the slope of the meson. So in some sense, it shows that, well, one thing that we found out that one cannot sort all the known resonances in meson trajectories. One needs also probably some other slopes, and maybe, well, I don't claim that it's a proof that there is a trajectory of globals, but it's an indication. The problem is that there is not much data in the region between 2.4 and 60 bar threshold. Now, I want to mention, since there was a question about whether how it depends on NC, there are additional possible closed rings which are based on adding DP and anti-DP. So, for instance, if this is the baryonic vertex and anti-baryonic vertex, and there is NC strings that connecting them, then the mass of such a global will be NC times the intercept, and the slope will be 1 over NC. So here, clearly, there is something which will not be the same for any NC, but very different for different values of NC. And then one can have, of course, a zoo of all kinds of possible closed rings that includes also baryonic vertices. Okay, I want to also now discuss this possibility of having tetracorps and pentacorps in these pictures. So let's talk about the charm sector. So this is a charm J psi meson 50 bar. This will be a cascade CC. So the baryonic vertex with two C quarks and U quarks on the other side. And there is, of course, no reason not to have a baryonic vertex and an anti-baryonic vertex with CC and C bar, C bar. And this is a cartoon of that. This is, for instance, a case where there is a C and a U on one side and a C bar and a U bar on the other side. And you can count that there are 225 possibilities of such tetracorps. Some of them are symmetric, some of them are semi-symmetric, and some totally asymmetric. And the main point that I want to make is that since they are based on a string, then there must be radial trajectories of these tetracorps. And once such a trajectory is discovered, so not only the ground state, but also excited state, that will be a clear indication that it's a genuine tetracorp and not a molecule. Now, there is such a particular example, and this is one example, and this is a state Y4630, which is predominantly decaying into lambda C bar. So we computed the trajectory, the state on the trajectory, and if they will be discovered, that will be indication that, and similar for the an object that can decay to lambda B bar. Now, another example that okay, so let me mention the sorry that there are in fact two types of possible decays. If the mass of this tetracorp is above the threshold of the baryon anti-baryon, it will be decayed by breaking. If it is below this threshold but above the threshold of two mesons, it will decay by annihilation process of the baryonic vertex and anti-baryonic vertex. And if it's below this threshold, it will be strongly stable. Now, using this, one can state precisely, I don't have time to do it, but the condition for these three possibilities, but we analyzed one particular system which was recently discovered. So there were two states discovered at 6.9 GeV and slightly above 7.2 GeV. This is above the threshold of cascade C bar, and this is this 6.9 is below. So we predict that this was not discovered yet, but that this channel should also discover to a baryon anti-baryon state. Okay, I'll end by flashing some predictions of higher excited states of mesons. So these are mesons with angular momentum that was not measured yet, and also radial excitations, and similarly for baryons with like nucleons with 15/2 J, and also with radial baryonic states. So since I ran over time, let me also now mention very briefly open questions. So to me, it's very crucial to have a method to to explain this negative A minus S. So this may require incorporating fermionic fluctuations. So we know that fermionic fluctuations are associated with negative intercept. Now, we still miss the quantization of string with charges when the total meson is charged. So when the two charges are not canceling each other, when they canceling, this is well known. This is the non-commutative geometry story of Zyber and so on. But when they are when the charge, like for the proton, this was not analyzed, then there is the problem of quantizing the string with spins. And when we want to, in this scattering process, we want to understand the total and partial cross sections, like for instance, the results of the total experiment. Let me flash my collaborator in this program. So thank you very much.
Thank you. So we have a few minutes for questions. So are there any questions to Cobi? So yeah, may I ask more about this negative intercept? Because so this intercept is really, it's a constant correction at large J to the rigid trajectory. But as you said, there is also correction which goes to J as J1/2, I think, related to the endpoint masses. When you're taking the difference between this A minus J, what happens to that other correction?
Well, so there are two types of corrections depending on where do they come from, the transverse or planar or Purkinje-Strominger terms. Now, the corrections that dominate, in fact, are the ones from this Purkinje-Strominger. The transverse and the planar are subdominant, but they come. I showed you earlier the form of this expression, and it comes simply when you by performing the classical quantization of this string with massive endpoints, provided that the masses are small. So it's not related. So it's just taking the basic. Yeah. So this is this issue, and
can you show the full formula, including that correction and the correction to the? Yeah. So there is this correction which goes like depends on the mass, which behaves as, if I remember right, something like J to 1/2. So for these J's which you see, can you really distinguish constant from J to 1/2? So when you say that it's intercept which is negative, for this small range of J, is it really possible to tell the two apart?
Well, what I'm presenting here is the result of this, as I said, quantum classical quantization of that. This, as you see, this is the PS, and these are the forms. Now, you are asking about comparing to the data and the.
No, I'm asking not about this quantity A. I'm asking about full expression for the rigid trajectory. Even there is classical correction to the rigid trajectory associated with the mass.
Yes.
Right?
Yes.
Which you probably showed before.
Yes. Here it is. So that's the general expression that we were using. We didn't take this. So these are the two limits of small masses and large masses. But when you do the fits, you take the general expression.
But yeah, if you want to rewrite it as 1/J expansion, then that correction.
Yes, you can translate this correction. I mean, this depends on small m over m, and which can be translated to J. So you can write it also as expansion in terms of J.
Yeah, so I think what you call intercept in this 1 over j expansion, that's a constant term in this expansion, and this correction is something like j to 1/2. So
Right.
the question is looking at the data. For that small range of j which you see, can you really distinguish j to 1/2 from constant term to claim that there is a negative intercept?
Yeah, well, from the fits, I can determine what is the, well, this is just going back to the fits. You can see that for each of these, clearly for this linear one, but also for this curved one, you can extract what is this quantity that follows this classic expression that I just showed you. And that is what we take A. This is what is the usual intercept. And then to relate it to the orbital angular momentum, I simply subtract this, the spin of the state.
Okay, maybe I should let other people ask questions. So Igor?
Yeah, like looking at the graph that's on screen now, which shows bending. Yeah, I thought often people plot J on the vertical axis and M squared on the horizontal, just flip this graph. And then I think we know that this Reggie trajectory alpha of T for in the negative T limit, it should match to the perturbative TCD, right? So it definitely bends a lot in the.
Well, that indeed happens, and this is the discussion of this paper that we wrote recently with Massimo Bianchi. So you can show that you go from a linear behavior at positive T to T goes to a constant when T goes to minus infinity. That is something that you get when you do this Polchinski-Strasser type of analysis of stringy amplitude. So what you start with strings in flat space-time, and then you dress them with a weight function, which is the function which is related to the spectrum of states in the holographic background, and you integrate over the holographic direction, and you see that you get this bending phenomena from linearity to a constant value for T goes to minus infinity.
Right, just to explain power law fall off at large energy. Right? Okay, thank you.
You're welcome.
Okay, I don't see any more questions, so let's thank Cobi again and